In this video lecture, we will state and prove the Borel Cantelli lemmas and start to give some applications of them. The motivation of why we would care about these lemmas comes from this characterization of convergence of random variables in terms of the measure of a certain event occurring infinitely often being zero. So here's the first Borel Cantelli lemma, which I denote as Borel Cantelli lemma 1. And it's the most important one, and it works for any measure space. And most of the times people use it in the probability spaces, but also on measure spaces. And it says the following. If we have a sequence of sets, measurable sets, which in a probability space would be interpreted as events, and we don't make any assumption whatsoever about dependence or independence of how these ANs are related to each other, if the measure of these sets is summable, then the probability that we see these events occur infinitely often, which is denoted by lim sup over n of an, that probability will be zero, which means almost surely we don't see an occurring infinitely often. And if we go back here to the previous video lecture, this is exactly what we wanted. We wanted to show that the probability of some event occurring infinitely often is zero. So we can see there's a good potential for this lemma to be extremely useful in practice. And the proof of the lemma is actually much simpler than to understand what it says and how to use it and when to use it. So let's write what is the measure of the sequence lim sup over n of an. So this is lim sup as n tends to infinity of an. This is just another notation for the same thing. And by definition, this is the intersection over n over the union of m larger than n of the sets am. And now let's just say when for each n, as n increases, this set is getting smaller and smaller because we're taking the union over a smaller family because we're starting later and later here. Okay, so the set in parentheses here, in green parentheses, is decreasing as n varies. And because it's decreasing, we can take its intersection. The measure of the intersection will be the limit of the measures. So from here to here, why is this equal? These are equal. This is continuity from above. And why can we use continuity from above? Well, because if the sum over n of the measure of an is finite, in particular, the measure of a1 is finite. So we can use continuity from above. And now, what can we say about the measure of this union? Well, we can use subadditivity, and the measure of the union is always bounded from above by the sum of the measures. Yeah, so here we have bounded from above because we're not making any assumptions about the ANs being disjoint. If they were disjoint, these would have been equal. But now, what is this? What are we summing here? We're starting at n and making n larger and larger, starting at n and summing all these measures here. So we have a series. This series is convergent. We have a series of numbers, indexed by natural numbers. We have a series. This series is summable. So in particular, if we only consider only the sum of the tail of the series, and we ignore the first n minus 1 terms, the sum of the tail is getting smaller and smaller. Otherwise, this series would not be summable, would not converge. Okay. So being smaller and smaller exactly means when we take the limit as n tends to infinity of the sum of this tail, which means we're summing more and more just the tail of the series, this limit is zero. This is true for any summable series of non-negative numbers. Okay? And that's exactly what is written here. This limit is 0 because this is the tail of a convergence series. So we're computing a number, and we just show that this number is bounded from above by 0. But well, of course, it's also bounded from below by 0. It's a measure. So it is 0.